Okay, well, hey, let's get started. So today's a Friday. Looks like we're lightly attended, but we'll post this online and we'll see what happens. Most of this stuff will be, this is a similar process that we're going to be doing all the next week too. So for those who aren't here, you'll be able to practice this process again and again. And we'll see what we do. All right, any questions before we get going? Anybody tried the homework yet? Not yet? Okay. Well, because we have a kind of a short day and because we probably won't get around to it till Sunday night, I figured I'd make it due on Tuesday, okay? I don't know if we'll try, I don't know if we'll get it all graded back by Wednesday, but I'll post the solutions as soon as you turn it in. So turn it in on Tuesday, maybe before, I don't know, before 4 o'clock at least. That way I can get it to the grader, and he might be able to grade it overnight and return it on Wednesday. If not, then he'll put it outside my box, or we'll have it outside my box so you can pick it up when you can. Okay? So Tuesday, 4 p.m., that's when homework will be due. And I'll put some more problems on today, like I said, depending on how far we get today, but I think we can get through what I need to. All right, any questions? Everybody happy? Everybody understand this stuff? I think we're pretty straightforward so far, but what you should be doing is compiling your list of equations. And I'm just going to back up just a little bit. And oh, wait a minute. It's not in this one. It's on this one. So let me see if I still got it. Yeah. Here's the list of equations I just copied out of the book. Where are they? No, I guess I didn't do it. No, I'm so sorry. No, I don't have them. Because this is dynamics, and this is that. Well, anyway, I started copying all the equations out of the book. So basically, just kind of write a list of them. You can have your own sheet of equations for the quiz on Monday. Okay. Probably won't be open book, but you should be able to have as many equations that you want on that quiz. By the time we get to the exam, I'm not really sure what we're going to do. Maybe we'll provide an equation sheet, or maybe we'll let you have your own. But anyway, start compiling your own equation sheet. Okay, so last time we talked about axial deformation. We derived our sigma equals FL over AE magic equation. We talked about the fact that deltas are the sum of all of those things, depending on what kind of configuration it is. We talked about that one, and we did that one. And then we did those which were just a little bit odd. So this isn't a big part of the course, but it's a good skill to know. I might be able to give you a small question on an exam. Sometimes on exams we do big questions, which would be kind of the most important questions, and maybe some small point questions, like 10-point questions or something like that, to see if you understand some of the minor concepts and that sort of thing. So this would not be a 25-point question, but I might give it a 5 or 10-point question on something like this to see how much you remember. All right, let's talk about axial loaded bar systems, or systems of axial loaded bars. All right, so this is pretty straightforward, I think, but if you're going to pull down on here, you're going to cause, okay, the concept of the rigid bar means that often there's some piece of this structure that, quote, doesn't change shape, right? It's rigid and it's made of some massive material compared to the rest of the stuff. Even if it does bend a little bit, it doesn't bend enough for us to take into account its own deflection. And we'll get to beam deflection and bending anyway, but for right now, that's a rigid bar. All right, so what do you suppose is going to be the deflection of those other two bars? What would you think? If I'm pulling down here, is this one going to be in compression or tension? Is this one going to be in compression or tension? What do you think? Yeah.
Tension for A and compression for B.
Yeah. So this is going to be, if you sum the moments about this point, that's a good way of kind of getting started. Or you can sum moments about the other one. But if I did that, I know that this one has to be going down, which means that this bar is going up. There's going to be tension in this bar. If this one, if you sum the moments about this point, then that force in this one has to be going up. So anytime you have force toward a joint, that is going to be a compression joint. Anytime you have force away or pulling away from the joint, that's a tension member. So what's going to happen is this one is going to deflect upward when it gets there. That's going to be the delta. And this one is going to be deflected downward. So that'll be the delta of 2. And then this one, because this one is a rigid bar, and what you do is you just kind of connect those lines like that, assuming I did that in a straight line. And now this one would be the delta of C, we'll call it. So something like that will happen. That make sense? So what we'll do is we'll do systems of similar triangles in order to find out what the total deflections might be. Now this particular one here, if this is now point C, this is now point D here, and D may actually have some of its own delta as well. In other words, it may be stretched, and so you may have not only the delta of C, but the delta of its own member that you have to take into account to find out what the total new position of D is. Make sense? All right, well, let's see if we can try it.
Are we assuming F is locked into the ground?
Yeah, F is it's a pin connection, and we'll call this well, you can't really have two pin connections like that without it being unstable. But in this case, well, let's see, we'll call it a fixed support. That'll work okay. And that way it's a stable structure, it doesn't tilt from side to side, and I think the equations will all apply to it. All right, so our process is we're going to use equilibrium using statics. We're going to use geometry or compatibility, and we may do some of this absolute versus relative. And what I would say is this is the absolute. In other words, that is the new position of that. And then this delta D is going to be equal to delta C. Let's put it this way. There is a textbook nomenclature called V, which means position. Okay? So what I want to say here is the position of D, V of D, is equal to delta C plus delta D. Does that make sense? We're going to have the new position of C plus this. Let me put it this way. Since that one's not a stretch, we'll call that V. VC, this is probably better. I think this is probably the way the book does it. Huh? All right. In other words, these two are changing position because of delta. This one is changing position just because it's a rigid bar. And then the new position of D would be the new position of C plus the stretch in the bar. Okay? So that's what I mean by absolute and relative. This one would be absolute, and this one would be some sort of a plus relative. We're also going to assume small angle deflections. In other words, at this point in time, we're not considering that these thetas are going to be very meaningful. We're going to use all small deflections, small displacements at this point in time. So again, a process, we'll start with equilibrium, then we're going to look at some geometry, and then we're going to do the force deformation equation for each part. All right, so let's try it. And where's my notes? All right, All right, so 516, figure 516, we have an aluminum link and a rigid beam. Actually, both of them look like they're aluminum, and the beam ABC is rigid. And link A has a cross-sectional area of 300 millimeters squared. Link 2 has a cross-sectional area of 400 millimeters squared. We're going to apply a load of 55 kilonewtons and determine the beam deflection at B. All right, before we even get started, let's imagine what it might look like. All right, so I'm going to be pulling down here. So this one is going to have some stretch in it. There's going to be some deflection. This is going to have some stretch in it. So here's going to be the new position of the bar. And so what we're looking for is this V and this delta, C and delta, we'll call that delta 1. Delta 1 because it's bar 1, and delta 2 because it's bar 2. The V is going to be the position, and there's no actual stretch, no actual delta that we're going to be doing there. That make sense? All right, let's see what we got. Start with statics, equilibrium. All right, so I'm going to find, I'm going to say sum of the moments about some point. So I'm going to sum the moments about A. And here I've got minus, let's see, P here says it's equal to 55 kilonewtons, so minus 55 kilonewtons times this 1.4 meters. And so that's going down. This one is going to be in tension. It's going to be pulling up. So I'm going to say plus force in 2. And the lever arm there is 1,400 and 800, so that's 2.2 meters. And that's equal to 0. So I can solve for the force in 2 is equal to 35 kilonewtons. And I can sum of the forces in the y is equal to 0. And I can find F1 is equal to 20 kilonewtons. All right, so nice round numbers on these textbook problems. That's nice. So those are the two forces that we need to start with. That's the way we get started. All right, next thing we do is, so I better put equilibrium. Equilibrium. Next thing we're going to do is the compatibility, right? So compatibility. All right, so that says that in this case, the compatibility is just this similar triangles look. So I'm going to say that delta here, delta 1 and delta 2, so let's say that delta 1, let's see, so there's going to be this, that, so B, B. This is going to be my similar triangle. It's going to take into account that delta. All right, so I'm going to say that delta 2 minus delta 1 over the total length is going to be this triangle right here. So that's going to be, the total length is 2.2 meters. That's going to be equal to VB minus delta 1 over 1.4 meters. So what I'm defining here is this distance here, that similar triangle, and then this one right here. Does that make sense? So let me get in here and I'll point to it. This is my, because it's pulling all the way down, this is one triangle right here, and then this is the other triangle here. So this distance here, VB minus delta 1 over this distance is the same as delta 2 minus delta 1 over this total distance.
What's V?
Sorry?
What's V?
V is a position, because there's not a stretch really associated. We use delta for the actual elongation of a beam or a bar or something, and so a position is just V.
Yeah, that makes sense.
Okay?
The
So
units
this
were
V minus the stretch in A1 is how much that distance is right there.
triangle set.
All right, so that's compatibility. Can't really do anything with that until we then look at the force displacement. So let's look at force displacement. All right, now here I do the delta is equal to FL over A of everything that does stretch. Let's see what that is. So we'll say delta 1 is equal to F1 L1 over A1 E1. And these are all in tension, so we don't have to worry about positives or negatives there. So let's see what I got. Actually, I know what F1 is, so I'm just going to put it in here. This is going to be 20,000 times L1, and that's going to be 2.5 meters. That's that distance. I'm given the area of link 1, and that is, this cross-sectional area, 300. All right, so that would be 300. Now those are millimeters squared, so to make it into meters squared, you have to divide by 1,000,000. So that would be E minus 6 meters squared times E of aluminum is 70. And gigapascals is E to the 9th. And so there I can calculate the delta there, and that is going to be 0.00238 meters. And you can keep it in meters or you can put it into millimeters, but I think meters works okay. All right, how about delta 2? That's going to be F2L2 over A2E2. And I have, that is going to be 35,000. It's got a different length, so that's 4 meters. It's got a different cross-sectional area, so that'd be 450. E minus 6. It's got the, oops, minus 6. And it does have the same modulus of elasticity of 70 e to the 9th. And I can get that is equal to 0.00444. Those are meters as well. All right, so then what do? We just plug them into the equation that works. And so I'm going to plug this one into here, and that one into there, and solve for VB. That's what we're looking for. So how did I do that? I just did it. I found delta VB was equal to 0.00369 meters. I'll let you guys crank through all the arithmetic. Okay. So this is kind of typical of a statically determinate system of bars. Statically determinate means there's no unknowns. We can solve the equilibrium equations with statics. And so these are fairly straightforward. And so now we're going to move into statically indeterminate structures, which are a little more complicated. But they're just as much fun. There's just a little more work. All right, any questions about this? Well, I guess we introduced a concept here of position is equal to a V, and delta is equal to a stretch. So if I forget and use V's and deltas interchangeably, they shouldn't really be interchangeable. They should be used properly here, but sometimes I'll forget, so you help remind me. All right. So let's just look at this picture here. What is the difference between these two pictures? This is the one we just did, or one just like. No, it is exactly the one we just did. What about this one? Why is this one statically indeterminate? Yeah.
We don't know how much force is going through each of the bars.
Yeah. Yeah, we don't know how to distribute the forces. We know that all three of those bars, well, I guess we don't know for sure, but we would expect that all three of those bars are going to stretch as you pull it down. But how much force to distribute to each of those bars depends on how much they stretch and what those materials might be. For example, let's say that the one on the right was a rubber band and the other two bars were steel, would you expect that the rubber band would take very much of the force? Or how much would it stretch? Not very much, right? Because it's not going to take very much of the force because it's made of rubber. How about if the middle one was a rubber band? Would you then expect most of the force to be distributed on the outside ones? Yeah. So that's the kind of a way that you can talk yourself into thinking that I can't really solve for those forces until I know what material they are and how much stretch they might endure. And so anyway, we're going to follow the same process. We're going to look at equilibrium. We're going to look at geometry of deformation. And then we're going to do force displacement relationships. The only thing we're going to add is the fact that we're going to put all of these things together into an equation and try to solve for the unknowns. And which equation we use, whether it be the force equation or whether it be the displacement equation, kind of depends on the situation. All right? So let's see what we got. We're going to talk about misfits and pre-strains next time. But we had some misfits that we talked about last time. Remember when a hole was maybe too big or something like that, and it would actually put the force on another member before it starts stretching on another, on one of the members? So we'll talk about misfits and pre-strains more later. But today, I think we can get to the fact that sometimes there's a gap. And like this one, there's a gap there and there, and so something has to expand and then fill up the gap. That could be a manufacturing defect. That could be just the fact of, whatever. Somebody just nailed it improperly. Might have a gap like that. We're going to actually go through this one today. So that would be a gap or a pre-strain. So concrete is a good way of thinking about pre-stressed conditions. Anybody know anything about pre-stressed concrete? Well, what pre-stressed concrete is that you actually stretch the steel, pour the concrete, and then let the steel go. And so the concrete is actually in compression at the beginning. And it just makes it a lot stronger when we do that. So pre-stressed concrete is a real common way of building in stress, the right kind of stress, before you even apply any kind of other kinds of loads. All right, let's talk about the process here. Again, we're just going to set up equilibrium equations. We're going to use geometry of deformation and do the force deformation relationships. I didn't put this in your notes. It's straight out of the book, but if you want to have some long-winded examples of what we're going to talk about, you're welcome to read those. Those are good. When we draw free body diagrams, we'll try to draw the free body diagram of the joint, and you can see that which way the forces go. As a rule, we're going to assume tension and assume a positive delta. In other words, we're going to mostly draw the forces. Even if we know that they're in compression, we're going to draw them in tension, and then we're going to draw all the deltas as a positive delta, even if we know they're going to be a negative when we get in. That way, when we solve for the forces, it'll be a negative force, and it should agree with our assumption. And when we solve for the delta, it'll be a negative delta, which will agree with our understanding, not the way we drew it. Okay? So we should get used to when we solve things to get negative forces and negative deltas. All right, let's see what we got. A bunch of different kinds of problems we're going to go through over the next couple days. Today we're going to do axial loaded bars, and we're going to do this gap one. All right. All right, so let's talk about this. Here is a concrete column that has a point load. Now, first of all, let's go back to what we talked about last time. What do we assume about arrows with point loads here? What are we generally assuming? We're assuming that all the force is concentrated on a little teeny tiny spot. What are we assuming?
Equal distribution.
Yeah, we're assuming an equal distribution using what principle? St. Benon's principle. So even if it actually sits on the column with a point load, we're assuming that with a very small difference in depth, just not very far down, everything's going to even out and it'll be evenly distributed. Another way of drawing this thing would be to put put a big steel plate on the top, like this, right? And then you could say that, then I'm going to push on the plate, and by the time it gets down to the actual work, it's already distributed, if you will, all right? But we're not going to focus too much on that. All we're going to do is we're just going to assume that it's evenly distributed and pretty nice. All right, let's see what we got. So we have a 670,000 Newton load on top of this column, and it's got 4 steel bars in it. This is concrete. We want to find the stresses in each of the rods and the stress in the concrete. Okay? Now, this is all built together as one assembly, which means that if it all shrinks together. So the deltas are going to all be the same. Okay? But the forces that how the concrete and how the bars distribute those forces are going to be a little bit different. So let's see what we got. First of all, let's do equilibrium. All right. So I'm going to say that the steel is going to be pushing up. And I'm going to say that the concrete is going to push up. So let's just say it here. The force of the steel plus the force of the concrete minus the 670,000 newtons is equal to 0. All right, that's all we can do for equilibrium. Let's talk about geometry. All right, here, the only thing we are talking about is what does the deflections look like? And all we're going to say here is that the deflection of the steel equals the deflection of the concrete. So that's just all there is. Deflection of the steel equals the deflection of the concrete. Everything's stuck together. Now we do force deflection or force displacement on each of the pieces. So we'll say force deflection. All right. I'm going to say that the delta of the steel is equal to the force in the steel times the length over the area times AE. All right. Let's first talk about areas. What is the area of the steel? Well, steel is rods. So let's see what we got. Steel.
Pi d squared over 4.
Yep, is equal to pi d squared over 4. And so these are pi. The diameter is 19 millimeters over 4. And I'll generally just keep them as millimeters, and then I multiply it by E by a million, because you got 1,000 millimeters per meter. You got that squared. And that's equal to 283.52 e to the minus 6 meters squared. Okay, that's the diameter of one. But I got 4 of them, don't I? So I have to put that 4 in someplace here. I can either multiply this by 4 right here, or I can put a 4 over here. Either way you do it, but you have to multiply it by 4. So I'm gonna put it in when I put the numbers in. So let's just put it this way. So this is going to be the force in the steel times length is 1.5 meters. And here I'm going to say, let me move this down a little bit since I'm out of room. All right, so I'm going to say 4 times 283.52 e minus 6. That's my area. And then the modulus of elasticity of the steel is 200 gigapascals, so 200 E9.
I have a quick question.
Yep.
Are you allowed to put the 4 with the equilibrium forces?
You put 4 times the steel?
Yeah, because technically you drew 4, right? Even though you are only showing 2 on that. Like the force is going up. Does that make
And then
sense?
just do it.
Yeah, okay, that's a really good question.
Then if it's only like representing like one total force of the steel, shouldn't there only
Yeah.
then be one arrow going up?
Okay. You can, I don't think so. The reason is because that geometry equation requires that those geometries get matched up. So let me proceed to the next step, and then let's ask that question again and see if it makes sense. Okay? So that's a really good question. Do I have to multiply the area by 4, or can I multiply the force up there by 4? And I believe that multiplying the area by 4 is the right way to do it. But let's proceed. So let's do the delta of the concrete. And we do the force in the concrete times the length times A times E, and that's going to be the force concrete, same 1.5. I got the area of the concrete. Oh, I didn't figure out the area of the concrete. Let's do that. A concrete is going to be equal to, well, I got a 250 millimeter square post, so that would be 250 times 250. However, what have I got? I got some rods in there, don't I? I have to subtract those out. Now, if the rods are really small, then it probably doesn't make much difference. But if the rods are big, then you clearly have to reduce the area by what is not there, right? So if it could be, it's basically a hole in the concrete. So I'm going to say minus 283.5 E minus 6, and I got the area of the concrete is equal to 61.36. 366 E minus 3 meters squared.
You would have to multiply 283 by
Yeah.
4.
Or
Multiply
there's
the
4.
area by 4.
I'm sorry, say it again.
You can
Four.
subtract 4.
You're right, times 4. Yep, there's 4 of them. Yep. In fact, this answer had the right factor in there. I'm glad you guys are paying attention. All right, so let's go ahead and put the area and the coefficient, or I mean the modulus of elasticity over here. So this is going to be 61.6, sorry, 61.36 E minus 3 meters squared times concrete is 29 E to the 9th pascals. And now what we're going to do is, I can't really solve for those because I have 4 unknowns. I don't know the deltas and I don't know the forces. So what do we do with 2 equations, 4 unknowns? Well, we start substituting and see what we can get. So the first thing we're going to do here is I'm going to substitute both of these guys into that. And let's see what we get. So let's solve this for one of the forces. I'm going to set this up. I'm going to say force of the steel times 1.5 over, and I multiplied all this stuff out. So I say that that is equal to 226.8 E to the 6th. And that's going to be equal to the force of the okay. I'm sorry. I'm putting all this stuff into those equations. Yeah, so this is the force of the concrete, and that's got 1.5 as well. And I multiplied all that stuff on the bottom there, and that is 1778 E to the 6th. And now I can get the force of the concrete is some factor of the force of the steel, and that is 7.840 force of the steel. Okay, everybody see what I did there? Just plug those things into that geometry equation. Now I have the factor, and now I have the force in the steel as a factor of the force of the concrete. And now I can plug it into the equilibrium equation and start solving for something. So now I solve this into that equation. So let's see what I got. So the force of the steel plus the force of the concrete, which is 7.840 force of the steel equals 670,000 newtons, and I can solve that for the force of the steel is equal to 75,796, and the force of the concrete is equal to 594,204 newtons. All right, so I don't want to go down too big of a rat hole here, but let's imagine that instead of multiplying the area by 4 up here, right there, I kept all those the same. What that would have meant was this would have been, when I set this would have been divided by 4. In other words, this would have been something like 50, whatever, about 55 e to the 6th. See what I'm saying? If this was 55 e to the 6th down here, then I would have got quite a bit different factor for the force of the steel. And plugging that into this, I would have got quite a bit different answers.
It wouldn't just balance out because.
Why don't you do it and tell me? Because I didn't do it, so I don't know.
Okay.
But it might be. It might be. Maybe you could multiply. Yeah, Rosalind, what's the answer there?
Well, I'm just curious, like, if you don't multiply the area by 4, you would have like 4 F steel plus F concrete.
Yeah, that's what you'd have to do. Is you could do, if you had a different factor here, then you'd have 4 F steel plus FC. Maybe you still get there.
But then your deltas are wrong.
But then the deltas would be wrong. Right, yeah, because then the deltas are wrong here, because then I want to solve for the delta using the actual force of the steel. I don't know, maybe.
You could make it work. if
Could you make it
threw a
work?
Factor for it, but you just have to like find a weird place to go.
Okay.
If anybody wants to play with this and tell me what the answer is, I'll work on this over the weekend and see how sensitive it is. See if you can do it both ways. But
Because I just sometimes don't know when you like add that factor versus when you don't.
yeah. All right. Well, tell you what. For now, if you have 2 materials, multiply,
Put it in with the
do the
area.
area.
Okay.
And here's a few more examples that we'll talk about. Things like this one, this column here, where it has a plate on one side and a plate on the other side. Instead of saying, well, you could multiply the area by 2 in this case, and I know that works. Seems logical that it would work by multiplying the force by 2 or the force by 4 in this, but
Aren't you just saying that the force, it's 2 different kinds of forces, right? Your original steel is all of the force acting on all of the steel.
Yeah.
And then the other one is.
just a single
all-
one.
It's just, yeah, single
Yeah.
one, so.
You took out or yeah, it doesn't work. You need all the area in the delta function.
I kind of think you need all the area to make this equation work properly in this. I think so. So for now, let's multiply the area by 4 and not multiply the forces by 4. We'll keep the force at the total, and if anybody can prove to me that it works the other way, then I'm happy to retract that. Okay, let's continue on. What we're looking for is the stress. All right, so now that I have the forces, it's pretty easy to do the stress, isn't it? All right, and then we want to get to the shortening. What is the actual shortening? So let's find the stresses quickly. That's pretty easy. We're going to say the stresses in the steel is equal to F steel over the A steel, and I'll just write you the answer. That's going to be 594,204, and then we have all of the area, so that would be 4 over 2, or 4 times 283 e to the minus 6. That gives me a stress of 66.96 E6 pascals. And then the stress in the concrete is equal to the P of the F in the concrete over the A of the concrete. That's equal to 9.68.
Isn't that's still 75,000, not 594?
Yes, beg your pardon, 75,000. Steve, 75,796. Thank you. All right, so those are the stresses. Now, the delta, you can choose either one. That's why, well, I don't know, I still think this is probably the best way to do it. But you can take these forces now, plug them into either one of those delta equations, and you should get the same answer. That makes sense? Yeah. David?
The 4 works. I just figured it out. It's all right, so you can have your 4 on the F steel. Your delta function has a factor of the force in it.
Yeah.
So if you delete that 4 and just add the 4 to that top equilibrium equation, you're fine.
If you divide that one by 4, and then you don't have to multiply that by 4, you should
Yeah.
get the same thing. So it probably should work. I just didn't do that.
It was bugging me. So
All right, so the delta then is this. Delta of either one is equal to PFL over AE, and I did it of the steel, and I got that is equal to 501 E to the minus 6 meters. So not very much, 500 microns that it actually moves down under this kind of a load. So most of these cases we're not talking about very big deflections, but they are real. And you get longer members, then they become a little more measurable, a little more important. So. Okay, this is an addendum to the class. I'm just visiting with Rosalind, our peer educator, and she did this work. I don't know if you guys can see this, but if you're careful with the forces and careful with the areas, then it doesn't matter whether you multiply the area by 4 or if you multiply the force by 4. But it kind of depends on the free body diagram. So if you look over there on the left, the free body diagram in the top one, the force of the steel is the sum of all the forces, and therefore you have to have the multiplied by the force, or you have to multiply the area by 4 in order to get the total force. If you look at the bottom one, then you have 4 separate forces, and therefore each force is going to be smaller, but obviously the area is smaller. But in the end, if you're careful, then you should get the same answer, and it shouldn't matter. And obviously, if it doesn't matter, then I don't care which way you do it. All right, hope that works. All right, let's do one with a gap. This is kind of a fun one. Here we have this assembly here, and it's got an aluminum, no, it's a steel rod on the top and a brass rod on the bottom. And we're going to put some force on there, and it's going to cover up that gap and then some. It's going to first stretch the steel till it stretches and covers the gap, and it's going to keep on pushing until it compresses the brass part. Okay? And what we want to do is find the stresses in both of those rods. All right, so let's draw a little bit of equilibrium business. Here again, what I'm going to say is that if you follow this technique, you generally won't go wrong. Draw the forces in tension. Draw the deltas as all positive, and then when you solve them, you'll get negative numbers for ones that you would expect that might be negative. All right, so I'm going to say that there's going to be a tension force here. I'm going to call that F at C, and I'm going to call this a tension force here, F at B. Now what we know is whatever happens here is actually what happens inside the rod. So I'm going to say FC is actually equal to F of 1, whatever's inside that rod. FB is also equal to F2, in other words, whatever's inside that rod. All right, so let's do the equilibrium. F1, it's called positive going in this direction. So I'm going to say equilibrium. I'll say F1 minus F2 minus this pushing force, and the pushing force is 65,000 pounds. So 65,000 pounds is equal to 0. A kip is 1,000 pounds. Those are both going down. The F2 is going down, and the pushing force is going down. All right, let's talk about the compatibility, or the geometry. Geometry, compatibility, those are kind of the same things. All right, what it's going to say is that there's a delta stretch of 1, and there's a delta of 2, and those are going to be equal to that gap. I drew them both as positive, even though I would expect that because the top one is in tension, it will get a positive number for that. Because we know the bottom one is in tension, that we should find that delta 2 will be a negative number when we get done with it. Okay? But together, they equal that gap of 0.125 inches. All right, now we do the force displacement equations. Force displacement. And those are pretty straightforward now. I'm going to say that delta 1 is equal to F1, L1, A1, E1, and let's see what I got. I don't know what F1 is, so I'll put that as a variable. The length here is 14 feet, and we need to be in inches, so I'm going to say 14 by 12, or times 12. The area of the rod 1 is given here as 1.25 inches squared, right there. And the steel is 30,000 KSI, which is 30 times 10 to the 6 PSI, so that'd be 30 E6. I think all those units will match up. Okay, let's, I didn't do any more multiplying there, so I'm just going to keep it there. All right, so delta 2. I know that this is going to be F2, L2, A2 over E2. All right, so let's, again, we don't know what F2 is, but here the length is 3 times 12. Here the area is 3.75 square inches. And the modulus of elasticity is 15 E6. And I generally will plug both of those into the geometry equations. Let's just put those in there, right there. So let's see what I got. I'm going to say that F1 plus that stuff on F2 is going to be equal to 125. So let's do that. F1, 14 by 12 over A1, E1. So I'm just going to shortcut this so I don't have to write everything again. Plus F2, 3 by 12 over A2, E2 equals 0.125. All right? Everybody okay with that? Because I just save a little bit of writing. And now I can solve this in terms of one or the other one. I solve this in terms of F1, because what I want to do is kind of combine them, put them in terms of another, and then put it back into the equilibrium equation. So I'm going to say here, F1 equals 0.125 minus F2 times 0.64 E minus 6 over 4.48 E minus 6. So now I have this in terms of F1. I'll plug that into that equation. And let's see what I got. All right. This one, now let's see. When I plug this in, I'm going to solve this in terms of this. So I'm going to say that this is equal to 29,902 minus 0.14285 F2. That's what this one is. Minus F2 minus 65,000 equals 0. Okay, everybody see what I did? Just did the multiply out, plugged it into that equilibrium equation. Now I can solve it for F1. So there's always going to be multiple equations, multiple unknowns, and it's almost always going to be a two-step thing here. You plug it into one equation, solve it in terms of some of the two forces in terms of the other force, or solve one of the forces in terms of the other force, and then plug it into the equilibrium equation and drive it. All right, so that gives me F2 is equal to negative 32,461. What does that tell you? This is going to be in pounds. Why did I get it negative? And does that make sense? Yeah, so you can see where I drew the force there. I drew F2 as a tension force, even though I knew it was going to be a compression force, didn't I? When I solved it to get a negative force, which tells me that I drew my arrow incorrectly. But this is just the way to keep things going crazy. So I'm going to say that F2 is equal to that. It is in compression. You don't have to write that down, but you don't have to do that on your answers, but basically it's just to tell us what's going on. Now if I plug that now into my, and solve it, basically, again, solve that thing, I'm going to get F1 is equal to 32,000. It's pretty close, the same, 32,539 pounds in tension. Yep.
Dumb question, but where do we get, what point are we looking at to get that equilibrium equation?
I'm drawing the equation for the whole thing. However, you could have drawn the free body diagram of that. In fact, I didn't do what I told you guys to do.
Why do we not need 2P? Why did we not need 2P here? Because this is P, right? And so we only took one of these?
No. There's P over 2 on each side. That's all.
Oh,
That's all what that
that's
says.
P over
Yeah,
2.
P over 2 on
Okay.
each side. They're just trying to
Gotcha.
keep the stress concentrations down by dividing it on both
Okay,
sides.
thank you.
So yeah, this equilibrium equation, the way the textbook does it, which I should have done it the way they do it, was draw a free body diagram of this part. So let's just draw a free body diagram of that part, assuming that they're mated together. And you'd get something that looks like this. You get negative 65,000. And then you're going to get something going up here. We're going to call that F1 and then F2. That's what it means by drawing a free body diagram of the joint, of the place where they meet together. Both tensions or both forces are going to be in tension that way if we solve it. All right, now that I've solved for F2 is equal to a compression force, which we expected, now we can solve for the delta. And that's kind of the more interesting thing, is what is the actual displacement of this point, of B? What is the actual displacement of B? Well, let's look at this. Let me just zoom in here and then I'll get back so you can finish copying it if you need. But the actual displacement of B is going to be, assume that that's very thin, but it's going to be the stretch of the bar, which is going to meet there, and then it's going to be the compression of that. Does that make sense? It's going to be the stretch of the bar plus the compression. So if I need to know what it actually changes, I have to add those two together. That's really where it's at. All right, so let's see what we got. Because the stretch of this guy is, well, actually, no. Let me think about that. Do I have to add them together? Actually, I don't have to add them together, do I? Because whatever the stretch of the top bar is going to go down, it's going to meet the gap, and it's just going to keep on going. And I have an equation for the stretch of the top bar, which includes all that junk. So all I have to do is just say the stretch of the plate, where B, the new position of B is basically just the stretch of the top bar. Includes all those reactions, includes the gap that I just overcame, and all that sort of stuff. All right, so let's say that the new position of B then is really just the delta of 1. So I'm going to say delta of 1 is equal to my force in 1, which is 32,539. The length of 1, which is 14 times 12. The area is 1.25, and E is 30 E6. And You get all that, and that's equal to 0.146 inches. Now that's pretty significant. That's over 1/10 of an inch. That's a lot. I mean, that's, of course, it's 14 feet long, but now we're seeing that it's actually something you can see. Now 1/10 of an inch is, you know, that much. You can see this, see the stretch in there. All right. Any more questions, or any questions at all about how we set the process up? How about you at home? Any questions? I can't hear you. That's nice. I like this. Yeah.
Students get to talk about it.